All right. So last time I was talking to you about this new sort of paradigm of solving physics problems, but in such a way that it doesn't involve at least as much vector stuff as you saw. Of course, the very first problem I tried to work was one involving the work done in pulling, done in pulling a box across the floor. And for that one, we had to actually do a free body diagram so we could figure out the normal force. So yeah. But anyways, yeah, there is some occasional work that has to be done algebraically, or excuse me, vectorially. But still, it's in general a lot easier. We're gonna further that now. I'm going to start off with introducing you to the work-energy theorem, and then I'm going to use the work-energy theorem to show you, in fact, that problem we worked last time with the box, a 20-kilogram box pulling at a 37-degree angle with a force of 220 newtons and a coefficient of static friction equal to 0.200. Excuse me, that was a coefficient of kinetic friction equal to 0.200. I'm going to show you that in fact gives us exactly the same acceleration that Newton's laws of motion do, even though we don't use Newton's laws of motion. So let's get started by first giving you an idea of the motivation of where the work-energy theorem comes from. And then I'm going to go from there and basically look at those answers we got yesterday or last time from the pulling of the box problem and go from there. Great. The yawning's coming again. It's so rude of me too. I don't mean it to be rude, but evidently I would think it is rude. Okay, so this is what we're doing. So what I want to do is I want you to recall that in some sense we could say work, and there's actually a way to do this with all the calculus stuff, but right now I'm just going to say that work net is equal to F net dotted with D. Or actually, we might not even say dot product. We might just say force times distance. Either way, that's fine. There is a way I can do this derivation using the full vector equation, work equals integral f dot dl and all that good stuff. But I'm working in such a way just to motivate what we're getting at. So what I'm going to do is I'm going to recall from Newton's second law that this F net that we're talking about is in fact the same thing as we called the summation of the forces when we talked about Newton's second law. And in fact, according to Newton's second law, that's equal to m times a, okay? So forgetting about the vectorness of it for a second, what I'm going to do is I'm going to say W net is actually equal to F net times D, where F net is the total force you apply to the object, and D is the displacement that it experiences. Now I will replace F net with the right-hand side of Newton's second law, which is M times A, and then of course that's times D. Now that's kind of interesting because we know from kinematics that we had this wonderful equation, the final velocity squared is equal to the initial velocity squared plus 2 times A. And we'd normally say x minus x0, but I'm just going to call it D because now you can see that with that, actually I can do it a little better. I can just say A times D is in fact equal to V final squared minus V initial squared over 2. So now I get W net is equal to the mass times V final squared minus V initial squared over 2, which I can make a little better by saying W net is equal to 1/2 m V final squared minus 1/2 mv initial squared, which I will call, since it is final minus initial, I'm going to take the liberty of calling that a delta something, as I've mentioned to you before. Delta always delta always means final minus initial. So I could just call this delta something because I've got final minus initial. And what I'm going to call it is KE for kinetic energy. So it turns out that KE is kinetic energy. And it's normally or often written as KE, but sometimes they'll even use T for it. But the main thing is it's defined to be, at least classically, when we get into special relativity, we'll see there's a different formula for it, but at least classically, it's 1/2 mv squared. And it's really an energy of motion. And in fact, Madame du Châtelet, who was the first person to basically translate Newton's Principia from Latin to a Vulgate language, if you will. In that case, it was French. She did this, if I'm not mistaken, I think she did it at the ripe old age of 16. She was a brilliant, beautiful young lady who, in fact, had as her sort of personal boy toy, if you will, at the ripe old age of her young 20s, a guy by the name of Voltaire. So she was pretty brilliant. Sadly, she died in childbirth at a very young age, but she was brilliant, and she called this quantity oomph, which I kind of like as well. So it's the oomph something has. So there's different types of energy that we'll run into, and this one happens to be the energy of motion. So if you want to think about energy in general, what I tell my students is, imagine energy as anything that has the ability to do work. And then when you think that work was, of course, the integral of F dot dl, you see that work is, of course, the ability to apply a force over some distance. So you might even think along the lines of driving a nail, and that's actually what I encourage, at least right now. Next semester, when we get into electricity and magnetism, you'll need a little bit more abstract ideas of work. Maybe work would be the thing that could cause an electron to speed up in going from one place to another, or even for a proton. But in this case, I want you to think of energy as anything that could be used to do work. And then I want you to think work is anything that could drive a nail. And that allows you, when you think that, I want you to allow yourself to consider not only, driving a 16 penny nail into a 4x4 or something like that. I want you to think of possibly the thinnest, most fine little nail with the sharpest point, maybe being applied or it pressed into hot butter, for instance. That would be fine as well. So when you get that, then you can see things like a molecule moving at a certain speed could, in principle, hit that nail and cause it to actually drive into the hot butter. And that's the reason that I allow you those extreme versions is to account for just such cases. Another case would be if I were to climb, say, to the top of a telephone pole, sitting up there on that perch. I would say I have an energy. In that case, that energy is associated with my position, and such energies are often called potential energies. Okay. Those potential energies are energies because they have, again, the potential to do work. So you could imagine, for instance, me falling off of a telephone pole, say, and landing on a nail. In that case, it could be actually a pretty good sized nail, and I would drive it into the ground because I'm, a pretty good sized guy. So that's another type of energy, and that one turns out to be a potential energy, and we're going to derive that in a second. But what we've come up with now is this new thing called kinetic energy. And you see that it's the energy of motion. That's why they use the word kinetic, because kinesiology or kines means motion. you can see that this has motion, partly because of mass, because if it was massless, it wouldn't have kinetic energy, at least non-relativistically, but also partly because of V. You, for instance, know that if a linebacker, inside linebacker from an NFL football team comes barreling in at you, you know they could do some damage to you. They can actually, in fact, do work on you, and you would think of that as some form of energy. But it doesn't take a really big guy with a lot of mass to, in fact, cause harm or do work on you or something like that. So there's got to be some other way other than just a large amount of mass. And that's where kinetic energy comes in, where, someone could obviously, accidentally throw a toddler at you and you can just, bat that down. I try to do these things to keep your attention, folks. I'm not really cool with babies. I love babies and toddlers and stuff of that sort. But if you throw that baby at me fast enough, it's not going to be so easy to deal with. In fact, that's exactly how bullets work as well. Bullets might often weigh a very small amount, on the order of several tens, if not 100 grams or so. And the reason why they do damage isn't necessarily because the M in kinetic energy, but because of the V in kinetic energy. So that if you go, instead of, let's say 100 meters per second, you go 200 meters per second, which is actually quite slow for a bullet, by the way. Then just going from 100 meters per second to 200 meters per second, in fact, increases your kinetic energy by a factor of 4 because of that V squared. So yes, the kinetic energy is something that's relevant. Of course, it does take into account mass, but it also takes into account more heavily velocity. Now, this thing that we derived that I wrote down here, that the total work equals a change in kinetic energy, that is actually a new physical principle, and it's called the work-energy theorem. So that's called the work-energy theorem. Now, I suspect every one of you is essentially sitting still as you watch this lecture. And I suspect on Monday you were sitting still as well. That being said, I know that the kinetic energy you had then was likely very close to 0. And I know that the kinetic energy you have now is very close to 0. Therefore, the change in kinetic energy between then and now for you guys is probably 0. So from that, I can conclude that all those forces that acted on you, the forces of gravity, for instance, pulling down on you, the force of gravity pulling you downward from the bed as you were getting up in the morning, or the force of gravity pulling down on you at night as you go to lay down in bed, the force of you and your legs being applied to the floor, the steps to climb up a staircase. All those forces are causing work, or actually doing work. And I can tell you definitively that total work since then, from Monday to now, is very, very likely to be 0. That's part of the power of the work-energy theorem. Another part of the power of the work-energy theorem is you could use it in principle to predict, for instance, how fast a vehicle was going when it got in a collision. So one of the things that you often see, or at least used to, this is going away a little bit now because we got anti-lock brakes, but whenever there was a collision, you'd almost always see skid marks going into the collision. And occasionally you'd even see a police officer with a trundle wheel, a wheel that actually measures distances along which it rolls. And you could take that wheel and roll it along the skid mark, and that would tell you specifically how long or how far the car was skidding. Now, in principle, you can take and look up the type of tires the car had. You can look up the make and model of the car and find out the weight of it. You can even account for, if it's a truck or a car or something carrying a buttload of weight, you can even count for that extra weight. Maybe it's packed full of steel containers, or maybe it's packed full of a bunch of fat physics instructors or something like that. You can take all that into consideration. And in fact, what you would compute is that those skid marks were in fact a friction force, just like the friction force we calculated on Monday. That actually caused a negative amount of work to be done. So you can take that, once you get the coefficient of friction between that particular model of tire with that particular normal force because of the weight of the car and everything that's in it, and that particular length, and knowing that the angle between the force and the displacement vector is about 180 degrees, you can come up with a total work done by the friction forces. That total work done is equal to 1/2 mv final squared, which in principle the skid mark should end with the car moving at 0 velocity, so that'd be 0 there, and then minus 1/2 mv initial squared. Therefore, you could solve for v initial and know the initial velocity of the car. That is more or less how we can make the conclusion that a person that got in a car wreck was in fact speeding. If we find that velocity turns out to be 70 miles per hour and it was in a 35 mile per hour zone, that person's definitely going to get in some trouble. So that's another neat thing we can do with the work energy theorem. But it basically just says if you take into account all the forces that act on a system, and from that calculate the total work done by all those forces, then that total work done will be equal to the change in kinetic energy of that system. So what I'm going to do is I'm going to use that to solve the problem that we did Monday. And I'm going to make use of those numbers right here. So first off, I'm going to go ahead and separate this from what we're getting ready to do. And I'm going to draw the problem that we had last time, which, if you recall, was a block whose mass was 20.0 kilograms. We had acting on it a force of 220.0 newtons acting at 37.0 degrees. And we also had that it was sliding across a surface and in fact went a distance of 40.0 meters and being slid across that system. And we had a friction force F kinetic, which equals mu kinetic times the normal force, where mu kinetic was equal to 0.200. That's basically what we had. Now, what we know is that the 220 newtons, at least in the x direction, in other words, 220 newtons times the cosine of 37 degrees, turned out to give us 175.7 newtons. Okay, that's carrying one extra sig fig, of course. And then we also had a vertical component of that force that was 132.4 newtons. So that's what was acting on that. Now we can draw a free body diagram, which I'm going to indicate with a positive y-axis here and a positive x-axis here. And then, of course, a negative axis these ways. Now, the forces acting on these things are, for instance, let's change my color to green for the positives. So I have a 175.7 Newton force going to the right, a 132.4 Newton force going upward. We have a friction force, and it's in the negative direction, so I'll use red for that. That friction force is F sub K. but I also have another positive force called the normal force pointing upward. The mass, like I said, was 20 kilograms. So that in fact gives us a downward and therefore negative weight equals mg, which is 196.0 newtons in the downward direction. That seems to be all the forces acting on it. So if we remember correctly, we can actually go ahead and calculate all these forces. But what we will recall is that the work done by the normal force, because the normal force is perpendicular to the displacement, well, that happens to be, even though we didn't work this part out, happens to be equal to the work done by gravity, mg, and both of those happen to be zero. So we know we've already taken into account those because they're already zero. However, we also found that the work done by the friction force was, in fact, in this case, we had a normal force of 63.6 newtons. We had a coefficient of static friction, or excuse me, of kinetic friction of 0.200. The normal force, like I said, was 63.6 newtons. And we knew the angle, of course, was 180 degrees, but the distance was 40.0 meters. And then we did cosine 180 degrees. And that gave us a work done by friction of negative 508.8 joules. And we also had the work done by the force. And the work done by the force, meaning that one that we pulled at 37 degrees, the work done by that force turned out to be basically 175.7 newtons. Notice that's parallel to displacement times 40 meters. And that gave us 7,028 joules. So that was all the work that was done on the system. So what I can do is now calculate what the net work was. So W net, what I want to know is, what is that? So that's the question mark. So now that I've gotten all this stuff down, written down, I can go ahead and say W net is equal to 7,028 joules minus 5, or it's actually plus a negative, by the way, but I'm just writing it as minus, plus negative 508.8 joules gives me, in fact, I might need to turn my calculator on, 7028 minus 508.8 gives me 6,519.2. 6,519.2 joules. Obviously, this was that 8 after the decimal place was a insignificant digit. You can see,
Professor, sorry to interrupt you. Where the how did you get the WF for well, yeah, the work final for
okay,
equals
yeah,
728?
I'm basically just pulling this from yesterday's notes, so you didn't actually see it. But if you take the summation, I'll do it right over here on the side. If you take the summation of the forces in the y direction equals mass times acceleration in the y direction, and you recall that this box shouldn't be bouncing up and down, therefore you get F normal.
Oh, I got it in the notes right here. Sorry.
Got it, no problem. 196 newtons plus, in this case, turned out to be 132.4 newtons. All that equals 0. That's where I ended up getting the 63.6. Okay. All right, so yeah, that's where all that came from. So now I've got that work net, and according to the work energy theorem, the work net is equal to the change in kinetic energy. Well, that means it's equal to 1/2 of 20.0 kilograms times V final squared minus, and I'm going to pull out the 1/2 m, and since it's common to both of them, minus what I'm going to call is the initial velocity of 0 squared. So now I can see that V final, at least according to this, should be, I'm going to take that 6,519.2, I'm going to multiply that by 2, and then I'm going to divide it by 20 because that's the mass. And then I'm going to take the square root of that, and I'm going to get 25.53. 25.53 meters per second. That's what the final velocity is according to the work energy theorem. Now, I would like to compare this to what Newton would tell us, but in order to do that, I either have to take Newton, get the acceleration, and then use kinematics to figure out what the final velocity is, or I can take this final velocity, use kinematics to figure out what the acceleration is, and then just work out Newton's second law and see if it matches the same acceleration. So I'm going to do that second one. You can do the other one if you'd like. But what I'm going to do now is I'm going to say that V final is equal to 25.53 meters per second. V initial is equal to 0. And we don't know time here. You know, it'd be nice. We could say A is equal to V final minus V initial over time. We don't know that. But what we do know is that A is in fact V final squared minus V initial squared over 2D. Because of that, I can say A is going to be 25.53 meters per second squared minus 0 squared, all that divided by 2 times 40.0 meters. Notice that's meters squared per second squared, divided by meters. So that just gives me meters per second. So 25.53 Okay, I squared that. Now I'm going to divide it by 80. And that gives me 8.149 meters per second every second. That's the acceleration from the work energy theorem. Now let's work at it with Newton's second law. So Newton's second law says the summation of forces in the x direction is equal to the mass times the acceleration in the x direction. Well, that's part of the reason why I took time to write down all those forces. What I see was that the force to the right was 175.7 newtons. So 175.7 newtons. That's the basically the x component of the 220 newtons. I also have a friction force, which I think was 12.72 newtons. I did not write that down here, so I'm going to go ahead and calculate it really quickly for you guys. Yes. So minus, remember the friction force is in fact mu k times the normal force. So that's going to be 0.200
I think that number is 12.72, so you can avoid doing all that.
Thank you. That's what I had. That's what I remembered as well. But yes, you're exactly right. Because the normal force was 63.6 newtons. So you're exactly right. Thank you. 12.72 newtons. That's all the forces acting in the x direction, and that's got to equal to 20.0 kilograms times A. So A is actually going to be equal to, if we do 175.7 minus 12.72, that gives me 162.98. Now I'm going to divide that by 20. And lo and behold, I get exactly 8.149 meters per second every second. So that's sort of our evidence that even though these are entirely different methods, evidently the physics is sound. We have a way where we can avoid a lot of vector calculations using, in this case, the work-energy theorem. And with that work-energy theorem, we can find the same parameters that we would with Newton's laws and his vector stuff. And in fact, they gave us exactly the same, even to 3 decimal places, which is beyond the number of sig figs that we were really entitled to use. So that 8.149 and that 8.149 is pretty telling. So anybody have any questions on that? And this way was from Newton's second law. Okay. So it turns out that is, in fact, a thing you can do. Now, I need some other forms of energy to make sense of what's going on. So I'm in chapter 7, but I'm also doing chapter 8 right now. So we already calculated, for instance, that the energy stored in the spring, which you might consider work done in compressing a spring, is equal to 1/2 kx squared. We might, consider that, but some people would also call this the potential energy stored in a spring that's either been stretched or compressed by an amount x. Either one's acceptable. The main thing is it's another form of energy. Another thing we have is kinetic energy, which is 1/2 mv squared. We also learned about dot products, and that basically is that A dot B, called the dot product, or also called the scalar product, can be given times by the magnitude of A times the magnitude of B times the cosine of the angle between them. But if you're going to use that equation, it has to be accompanied by a diagram to make some sense of what it means. And the sense is that if you have the two vectors A and B tail to tail, then theta is the small angle between them. Now, it also happens that A dot B can be given by A sub x times B sub x, meaning the x component of A times the x component of B, plus the y component of A times the y component of B, plus the z component of A times the z component of B. So that was something else we found. And now we found that W net is equal to the change in kinetic energy. So that's really wonderful. We found a lot of neat new things. However, we need a little bit more. I've hinted to you that another form of energy is a energy that has the potential to do work, and it was related to position. So what I'm going to do right now is I am going to imagine an object sitting on the ground with a mass m. Okay. And what I intend to do is something I'm going to do very, very slowly. What I want to do is I want to apply work to this mass in such a way that I actually lift it from the ground level all the way up to, say, this height h right here. But I want to do so without actually contributing anything to its kinetic energy. In other words, I don't really want it to speed up or anything like that. I want all of my energy, all the work that I'm doing, I want to calculate exactly what that is. And I want to do it in such a way that I'm only lifting this weight, this mass m, up to a height of h. So the way I'm going to do it is this. What I know exists, at least in the vertical direction, I'm going to have a mass m. Acting on it will be a force mg, which is the force of gravity. And then also acting on it will be the force that I apply, F. Okay. Now, what I want to do is apply just enough force where it's free to accelerate, but because I don't want to accelerate it, I don't want to speed it up, I'm not going to give a single bit more force to it. My plan is, in fact, to bring it into equilibrium where it's free to move, and I'm just going to wait for, say, the random molecule or gnat or flea or fly to just happen by and bump into the bottom of the ball so that it moves up a little bit. And though that may take 100 years, I don't care. I'm willing to wait. Okay. And then I'm going to, again, by keeping my hand under it, I'm not letting it lose any ground, but I'm slowly letting all those little bumps of molecules, gnats, flies, whatever, mosquitoes, I'm letting all of them add up until eventually, some years down the road, I've actually moved the mass to a height h above where it started. Okay. So in doing that, what I can see is that work is going to equal the integral of f dot dl, but in this case, the f is going to be a constant. In fact, the f is going to be mg j hat. Remember, j hat's the unit vector that points in the positive y direction. So that's the force I'm applying to it. Notice it's just barely enough from the summation forces in the y direction equals mass times acceleration in the y direction. And I want the acceleration equal to 0. That means F minus mg is equal to 0. So F is equal to mg. So that's why I use that. Now I'm going to dot that with a little line segment that's going vertically. So I'm going to call that dy j hat. Now that's going to just become mg, because that's a constant, times the integral of dy, and the dot product is a linear operator. So that just becomes j hat dot j hat, which, using our definition of the magnitude of a dot product above, you can see that's 1 times the cosine of 0. So that's just 1. So ultimately, I get just plain m times g times h. And that's it. It's called the potential energy. So potential energy, which, by the way, is often sometimes used as a U, is equal to mgh, and it is up to you to choose what you think is H equals 0. Okay. What I mean by that is imagine, for instance, today I was teaching in the second floor of J building, the science building. And anybody in the class would have seen me hold up a pen a little higher than my head. So we might say, you in the class might look at that and say, okay, well, the pen's 2 meters off the floor. So we're calling H 2 meters. Therefore, the kinetic or the potential energy that it has is M times G times 2 meters. That's fine. Okay. But someone else from outside might be looking up at me and saying, oh, well, look at that. Mr. Younger's holding that pen. And it appears to be, in fact, 5 meters above the ground, because their ground is obviously down on the first floor. And you might estimate the distance from the floor of the first story to the floor of the second story to be about 3 meters. Then from their perspective, I was holding up the pen at a height of 5 meters. Now, you might think, okay, well, that's going to mess everything up, but really it's not, because when I drop the pen, I'm going to drop it and it's going to go from, at least in the classroom, it's going to go from mg times 2 meters to mg times 0 meters. And that means the difference is final minus initial, -2 meters times mg. Well, in the case of the person outside, they saw it go from, in fact, 5 meters to, in fact, 3 meters. So they'd say it is, in fact, 3 meters times mg minus 5 meters times mg, which again will be -2 meters times mg. So you see they get the same change in potential energy, which is really what's going to dictate what's the velocity, because if you allow a pen or a ball or something to drop, as the potential energy decreases, the total mechanical energy, assuming you're ignoring air resistance or there is no air resistance, the total mechanical energy is being conserved. So every joule of lost potential energy becomes a joule of gained kinetic energy. So all that really matters is the change in potential energy. And that's just a feature of scalar functions. You can add a constant to any scalar potential and it's not going to change the problem. In fact, there's a whole bigger story behind all that, but the deal is you can add any arbitrary number to a potential energy function and you're not going to change the way it behaves. Okay, so we now have a new equation to go with our old ones, and that is potential energy is equal to mgh, and I'm going to say close to Earth. In other words, what I mean by that is close to the Earth's surface. It turns out that does not work. For instance, if we shoot off the face of the Earth and go out about 30 Earth radii, in other words, go out to maybe half the distance to the moon or something, then that equation doesn't work. In fact, the equation that works when you have that scenario is, and we're not learning about it yet, you'll learn about it in chapter 8, but basically the potential energy in that case, you don't have the freedom when you do this one of choosing where the 0 of height is. This one we have to choose, because of the nature of the law of gravity, we have to choose that the potential energy is 0 at r equals infinity. And in doing so, we get -g times the mass of the object times the mass of the planet divided by the radius of the planet. And yes, it is to the first power there, because that's what happens when you integrate r to the -2 power. So we now have this litany of different equations that we can use in addition to this one I didn't even write down. let's say,
Professor, why is it negative for the potential energy off of the like surface of the
yeah,
planet?
that is actually a weird thing, but it turns out it has to be, because basically when you push an object out to infinitely far away, we have to have the potential energy be zero. And then when you get closer, you have to have it smaller than zero, namely because it's, well, you've got to have its magnitude. Let's put it that way. Its magnitude's got to be negative so that you can get closer to it. That's sort of the way of looking at it. I will tell you, it basically comes from integrating this work equals the integral of f dot dl and setting the, basically you integrate it from r equals infinity down to r wherever you're at. And in doing so, you have to say r equals infinity corresponds to potential energy equals zero, and that forces the negative to be on there. It's kind of a pain, but when you actually try to work with it, you'll see that it actually works out nicely, because it keeps you from getting like negative velocity squared and stuff. But that's a good question. It is kind of a pain that way, but anyways, here's our new sets of equations, if you will, that I just have introduced over the last 2 days. And this is covering essentially chapter 7 and chapter 8. So we have all these new figures, the work-energy theorem, which I've put right here. We've got this new concept of potential energy. There's other forms too. For instance, there's energy associated with chemical energy. You can get, for instance, two atoms too close together. That actually increases their potential energy. You can get them too far apart. That could actually increase their potential energy. There's all sorts of different types of energy. What I do, okay, your book does this quite differently, but what I use is this equation, and I'll tell you why it's useful in a second. So this equation you will not find in your textbook, but you are allowed to use it on your equation sheet. And this is what I do. I will say, let's write this in blue. I'm going to say the conservation of energy equation is work in plus the initial potential energy plus the initial kinetic energy is equal to the work out. So that's work done on the environment by the thing, plus potential energy final, plus kinetic energy final, plus E loss. Okay. What I have found, literally since being an undergraduate and taking the algebra-based course for this, I have found that this equation works best for me. And despite my OCD, I do not mind the fact that the left-hand side has 3 terms and the right-hand side has 4. And the reason why is because these terms are not necessarily single terms. For instance, that potential energy. Remember earlier I showed you that people think sometimes of this 1/2 kx squared as if it's a potential energy in a spring, but other times people think of it as the work done in compressing a spring. Because of that, I know that that potential energy could be mgh, but it also might be mgh plus 1/2 kx squared. Okay, so each of these terms, though they have some statement and names, they actually can be covering a lot of different things. The main thing to keep straight when you use this version of conservation of energy is that every form of energy has to be taken into account exactly once. Okay, now what your book and other books often do is they'll normally just say something like the change in kinetic energy plus the change in potential energy is equal to 0. And that's essentially right. It just doesn't give you any ability to take into account, let's say, a father giving his child a push at the top of a snow slope, like a ski slope. Like if you're going to allow your kid to ride on some snow skis or a sled or whatever, then the father might actually want to give the child a push. Well, you can't take that into consideration with that version of conservation of energy because it only has potential and kinetic energy. What if you want to take out or take into consideration the fact that there's going to be some friction between the slope and the actual snowboard, for instance? You can't take that into consideration with this version in the red either. You can't take into account if the child, for instance, runs up against a spring-filled bumper, a spring-loaded bumper, and compresses it. You can't do anything like that. So this version in blue allows me to take all those terms in. And in fact, the E loss could in fact mean 4 different terms. Work in can be 2 terms. It could be work in plus what you normally call E in if you wanted to. That would be fine. So that's the main reason I use this. It allows me to do all that. Let me show you a example of how it's used. And it's sort of a one-time hits everything example so that you don't have to see a bunch more to understand what the terms are. So, and I make up the numbers, so really bad stuff can happen here. So this is okay, but not what I use. And I just realized I can't remember how to spell recommend. RECCOMEND. I want to put like 4 C's and 4 M's in that, but I don't know. So anyways, so let's imagine a scenario. Here's the scenario. I am going to say we have a slope, and first it's level, and then it becomes quite rough, and then it runs into a spring-loaded bumper. I'm going to say this distance right here is, let's say, 50.0 meters, and let's say mu is equal to 0.700 there. I'm going to say there is a little sled here with a small child on it. Okay. The mass of the small child plus the sled is 45.0 kilograms. And I'm going to say that dad is putting a force equal to 100.0 newtons, and he's going to do so over a distance of 3.00 meters. Okay. Notice the force is horizontal, so I don't have to worry about any of that stuff. The rest of the surface, by the way, is frictionless. Now, if the little rumble area that's 50 meters long, you can sort of think of that as the safety exit ramp that you see in the mountains for Mack trucks. You know, when Mack trucks become runaways, like their brakes have gotten too bad off, there's like a emergency off ramp for them to pull, and it's like really deep sand and stuff. That's sort of what we're pretending like this is. I'm going to say, and just making these numbers up now, I'm going to say this is 200.0 meters high above this spot. Okay. So first thing I want to know is right here, what is the velocity of the sled? Then if the velocity of the sled is big enough, I want to know exactly how far X the child will go across the rough surface before they come to a stop. Now, if I find that the child will go way beyond 50 meters, then I know the child's not coming to a stop and is then going to run into the spring-loaded bumper situation. And in fact, I know that the K for this spring-loaded bumper situation is equal to 7,000 newtons per meter. Okay, in which case I wish to know x2 equals question mark. Okay, so that's what I'm trying to do here. Now, what I know is, since I'm starting to look at it at the instant the father pushes the child from rest, then I know kinetic energy initial is equal to 0. I know that the work in, which is what the father's doing, is going to be 100.0 newtons times 3.00 meters plus 45.0 kilograms times 9.80 meters per second times 200 meters. Now, what term is that? Can anybody tell me?
What do you mean by what term is that?
Out of these, one,
Newton
two,
meters?
three. What'd you say it was?
Newton meters?
The units are Newton meters, which is a joule. But do you know which one of these 7 underlying terms that 45 times 9.8 times 200 is?
Kinetic energy?
It's actually the potential energy. Let me show you. Remember this guy right here? P E equals mgh. That's what I just did. M times G times H. So I'm just trying to keep you guys straight so you know what I'm doing. There's the potential energy initial. Now, the kinetic energy initial, like I said, was 0. So I'm going to say plus 0. All of that is going to be equal to, now, in this case, I'm just trying to figure out what the final velocity is. So the work out's going to be 0. The potential energy final is going to be 0 because I'm going to call that level ground at the bottom H equals 0. And in fact, the kinetic energy final is what I'm looking for. That's going to be 1/2 times 45.0 kilograms times V squared. And that V squared is what we want to know. So this is what I'm calling part A. This is what I'm calling part B. And this is what I'm calling part C, even though you might not be able to do B or C if A works out a certain way or B works out a certain way. So what I have to do is I now have to take 100 times 3 and then add to that 45 times 9.8 times 200. And that's going to give me 88,500 joules. And that is in fact equal to 22.5 kilograms times V squared. So for part A, I'm going to say V is equal to, I'm going to take this 88.5 and I'm going to divide it by, and that's 3,933. So I'm going to say square root of the answer. Whoa, I don't know what happened there. And I get 62.71. Oh, this is not a good situation for the small child. Okay, so that's on the order of like 140 miles per hour. The child's going to be fine. Trust me, she'll be fine. Okay. She's going like 140 when she gets to the rumble spot. That's a suboptimal outcome. But anyways, all right, now we're going to do part B. So what we've now seen is that clearly the child has a buttload of velocity when they get to the rough part of the snow. That's hopefully going to slow them down before they run into the catch-all spring-loaded bumper situation. So I can either say right now, all I have is kinetic energy initial is the only thing that's not zero. The potential energy initial 0, the work in is 0, the work out is 0, the potential energy final is 0. And what I need to figure out is if I put the kinetic energy final being 0, how far will the actual child go? In other words, what is X before it comes to a stop? If that X is bigger than 50 meters, then I know that rumble spot's just not big enough. So I could do all that, but really all I have to do is set it equal to the initial energy, which is the 88,500. So I'm going to say 88,500 joules is equal to, in this case, 0 for the workout, 0 for the potential energy final, plus 0 for the kinetic energy final, because I'm pretending that the rumble area, the rough area, is long enough to bring it to a stop, just so I can see if it needs more than 50 meters. So I'm going to say the E loss is in fact the child, since the child's not on an incline, there's no extra forces pushing down or up. The normal force is just going to be mg. So the friction force is going to be mg times mu, and the work done is going to be mu times mg times x. So I'm going to say 0.700. That's the coefficient of static friction, times 45.0. I'm going to leave off the units here, times 9.80. So that's just the friction force. Now I'll multiply that by X and solve for X. So I take the 88,500 and I'm going to divide by parenthesis 0.7 times 45 times 9.8. And that's going to give me, in fact, 286.7 meters. So clearly the rumble area or the emergency off ramp that we left for the Mack truck, it's not big enough. That'd be particularly problematic. If you've ever looked, some of these emergency escape ramps for trucks literally end in like a cliff and a straight drop. But trust me, they've worked out all the details so that they know unless the truck was going something like 1,200 miles per hour, there's no way it's getting through that. All right, so we figured out that in fact it's going to go the full 50 meters and then it's going to start compressing the spring. Now what I've got to do is, again, assume the final kinetic energy is 0, the final workout, the final, well, I could use workout or E loss to count 1/2 kx squared. Doesn't matter which one. The main thing is I've got to take into account 1/2 k, what I've called x2 here, squared. So now I'm going to do the same thing again. This time I'm going to say, okay, I have C, which is where we're trying to figure out x2. The initial energy is 88,500 joules. I'm going to actually count it as workout. So I'm going to say 1/2 times 7,000 newtons per meter times x2 squared. That's the total energy that goes into it. I'm saying that's being added to 0 for the final potential energy, 0 for the final kinetic energy, but there is a E loss that I got to take into account, which is 0.700, 45.0, 9.80, and then of course the actual 50 meters that it can go. And I've got to solve for x2. Okay, so what I'm going to do is I'm going to take my 88,500. So here's the part where I'm not actually writing it down. I'm actually saying it. So you might want to listen or record it, or, you know, go back and mark this on the video of somewhere where you want to listen to. I'm taking the 88,500. The first thing I'm going to do is subtract from it, parenthesis, 0.7 times 45 times 9.8 times 50. Notice how all my signs are positive in these terms. That's another perk with this version of conservation of energy. Other than using that crazy U equals negative GMM over R, which y'all asked about, everything's going to be positive here. So you don't get, you know, sometimes you just get confused when you're trying to make sense of whether the energy is positive or negative. That doesn't happen with this version. So now I've taken that 88,500 and I've subtracted the E loss due to the rumble strip, if you will. And now that gave me 73,065. So 73,065 joules is how much energy I have left. I'm going to multiply that by 2 and then divide it by 7,000 and then take the square root. So I'm going to say times 2. Now I'm going to divide it by 7,000. That gives me 20.876. Now I got to take the square root of 20.876. And that gives me 4.57. So in fact, this, if you assume that that spring-loaded bumper was really a spring-loaded device meant to go a large distance, as opposed to a bumper, which really is not meant to go very far at all, then the child will actually compress the bumper by 4.57 meters in order to bring the child to a stop. Okay, but I think this particular example is good because I've shown you now how to use all the possible terms, or at least a way of considering using all the possible terms. Does anyone have any questions about that? Okay, so there's a deeper mathematics and science and physical concept at work here, and I want to give you that insight. Your book does it in a couple paragraphs, so I too want to cover it. I will tell you that you'll get more experience with it next semester, and this will actually help because you'll have then seen it 2 times. But this is the deal. There exists a certain type of force, or force field, you might call it, such that you can create a scalar to represent it. In other words, force, which is a vector quantity, and a force field, which would be a vector field, has a magnitude and direction at every point in space. And in order for you to work with that, you generally have to do vector mathematics. You have to, take into account the x components, the y components, and the z components, and only add like components and only subtract like components and all that. And then in the end, figure out a magnitude and direction. But there exists a certain class of forces such that you can represent them with a scalar potential, like we did here with potential energy. And when that's the case, you can work mostly with just scalars and it all works out. So what are those cases? Well, it's a neat thing. It turns out that if you prove any one of these things true, then all of them are automatically true. And that allows us a great deal of freedom, and it gives us some insight into the science of what's going on. So what I'm going to tell you is, if you have mechanical energy such that energy is conserved, then we name such forces conservative forces. So issue 1 here is going to be 1 F of, let's say, X, Y, Z, and maybe even T is a conservative force. That's one of them. And in fact, it's just a name. So really, I wouldn't even have to include that. I just do it because it's a freebie. Okay. If that's true, then all of the things below are true, which we often write by showing a implies with a double arrow. 2. Now, this is kind of weird, but it's something called the curl. So if you take the special operator, which I've hinted at you before, it's basically an operator that's meant to put anything to its right. If you get far enough in Calc 3, you will cover this and you guys will call it a gradient. You won't call it an operator, but in some sense, it really is an operator, in that I normally would draw this triangle with like a little underline bar, just saying, hey, something can go in here. And then I'd say equals, and I'd write I hat, the unit vector pointing in the x direction, and then I'd write the partial derivative of nothing with respect to x. And then I'd say plus j hat, and then take the partial derivative again of nothing with respect to y. And then I'd say plus k hat times the partial derivative with respect to z of nothing again, because it's all meant to act on whatever's to the right of it. That's the gradient operator. And if you decide instead to use that vector operator as the second row in a matrix, the first row of which is I hat, j hat, k hat, and the third row of which is that force function above x component, then the y component, then the z component, then you have something called the curl, which is del cross f. If this del cross f is identically 0, okay, if that's 0, that turns out to be the real test of whether or not this f is a conservative function. Okay, this quantity, by the way, is called the curl. It's also called the rotation. I've seen it written that way. And as I said before, it really is the determinant of a matrix whose first row is I hat, j hat k hat, whose second row is the partial with respect to x. Notice how I'm writing it without the whole fraction just to save space. Partial with respect to y, partial with respect to z, f sub x, f sub y, f sub z. That's what that curl is. Okay. Now, again, if that's true, then this below is also true. And it is that if you have the integral from a to b of f, actually, of f of x, y, z, t dotted with dl, then that is in fact going to be equal to u of b minus u of a, no matter, actually, I don't know what's going on here. It's writing funny. No matter what path is used to go from A to B. In other words, remember I told you that work equals the integral of f dot dl is technically a path or line integral. What this is saying is if you go from the initial point to the final point, it doesn't matter which path you take. You can find the easiest one and do it. This comes in really handy later. We'll learn that entropy is just such a function, and there's no good way of computing the entropy along the path that it actually takes, but you can pretend it takes a path along an adiabatic process, and from that get an actual result. And since it doesn't matter what path you take, your result is guaranteed to be true, or to be right. So that's another thing that's really helpful. There's another one as well. Again, all these, any one of them imply all the other ones are true. This one basically says that the integral over any closed path, in other words, instead of starting at A and ending at some other point B, if you start at A and do anything you want but end up at A, then you've got what we're showing here, which is an integral with a circle on it. That integral of f of x, y, z, t, say, dotted with dl is actually equal to 0. Okay. And here is really the most important part, and this is mainly why we bring it up here at all. I'm going to write it in some fancy mathematical terms so I can save myself the writing, but also so y'all become familiar with them. So first off, I'm going to write an upside down and backwards E, because the upside down and backwards E means there exists a scalar function U such that, notice that looks like a fancy cursive S running into a fancy cursive T. So I'll write what that is. This means such that F, the actual force of X, Y, Z, T, say, is equal to the negative gradient of U. Okay. So let's look at that in terms of what we just did. So So here's an example. Okay, class is actually technically up at 6:42. I want to show a quick example on here. You guys are free to go, of course, but earlier we found that U was equal to mg, and if I oriented the y-axis accordingly, instead of h, I could just call it mgy. And that would be the scalar function. That's the potential energy function for the force of gravity, which is a conservative force. Okay. Now, this operator that I showed you, this del thing, that is in fact I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. And it's not that big of a deal. All you do is when you're doing a partial with respect to x, for instance, is you pretend like y and z and any other constant and any other variables are constants. Okay. That's the only difference. It's not that big a deal. I'll even show you a definition on the next page. Again, that'll be on the video, but you don't have to watch. So if you take the derivative of u with respect to x, that's the partial derivative with respect to x of m times g times y. So m, g, and y are all constants. So what's the derivative of a constant? Anybody?
0.
0, right? How about the partial derivative of u with respect to z, which is the partial derivative of, actually, let me take that part out. Partial derivative with respect to z of mgy. What do you get for that one? Again, m, g, and y are all constants with regards to a partial derivative. So we're going to get 0. So now I'm going to use this actual formula right here. So I'm going to say F is equal to the negative gradient of U. Well, that's the negative. We've already worked out 2 of them. The one we haven't worked out is the one that we know is not going to be 0, which is this guy. So I'm going to say J hat partial with respect to Y of MGY. Can anybody tell me what the derivative of MGY with respect to Y is?
mg.
Exactly. So you're now going to get negative mg, and lo and behold, it's even wise enough to know that it points in the negative j hat direction. Booyah. Okay. So yes, that's a truism. Okay. So anytime you have a conservative force, then that means it allows you to find a scalar potential that you can use. And this is all from coming from that. That's it. That's all I wanted to cover with you guys. I will, like I said, once in case anybody has any questions, I'll go ahead and show you the 2 definitions of a derivative versus a partial derivative. So you'll see the ridiculously similar aspects of them so you can make sense of it. But literally, I'll tell you guys, when you're doing a partial derivative as opposed to a regular derivative, you can literally, if you're taking the derivative with respect to x, you can take every other variable other than x and replace it with one of them with a 2, the next one with a 3, the next one with a 4, the next one with a 5, and keep on doing that. And long as you don't intermix them and cancel things out, you can then, when you're all done taking the derivative, you can put in the 2, the 3, the 4, the 5 in for the variables that they were replacing, and you will get exactly the right answer. So it really is that straightforward. So anybody have any questions before you split? Remember, we have all next week off. That's from the 5th to the 12th is spring break. We're going to have your exam. In fact, on the 15th, when you return, that'll be the Wednesday after you return. Ideally, you should all be prepared to start like 25 minutes early or end 25 minutes late, or basically split the difference even. You could do 10 before and 15 after, or 15 before and 10 after, or whatever. If any of you cannot do that, you need to let me know, because I'm going to have to find some other way, or I'm just going to choose to make your exam only last an hour and 20 minutes. So any questions, Kamna, Didio, Gavin, Taylor, Alex, excuse me, anybody?
No
Randall?
question at a time.
You do have a question, sir, Kamna?
I said no question.
Oh, none at this time. Gotcha. That's good. Anybody else? Mariana, any questions? John, Jared? Thank you for coming, everybody. I hope you all have a nice, peaceful break. I've given you some lenient deadlines for the next homeworks and test 3 even. So, take advantage of that. Take your time. Try to do a little bit of physics every day. That's what's best for you. But do, relax and have a good time. Anyone?
Have a good break, Mr. Younger.
Thank you, John. Appreciate it. I assume that was John, actually. Alvin.
Yeah, it was me. It was me.
Okay. That's cool. Alvin, you have any questions, or Mariana? Mariana, probably. All right. Well, I'm going to go ahead and explain the definition difference between the two derivatives. So when we have y equals f of x, then George Walker's coming in. Okay. When we have y equals f of x, then we have something called the derivative of f with respect to x, which is the limit as delta x approaches 0 of f of x plus delta x. That literally means, hey, everywhere you see an x, replace it with x plus delta x in parentheses, minus the original function f of x, divided by the change in x, which in this case is final x plus delta x, minus initial, which is just x. So that's what the derivative of a function is if the function has one variable. If the function has multiple variables, let's say y is equal to f of x, comma, y, comma, z, and in fact, maybe I don't even want to call that y, maybe I call that u or something. And maybe I even change the color of the pen just because I'm a goober. Let's say that's u. If that's the case, then we define something called the partial derivative with respect to x, which is really going to be the limit as delta x approaches 0 of, in this case, it's going to be f of x plus delta x, comma, y, comma, z, minus f of x, comma, y, comma, z, over x plus delta x, parentheses, minus x. So you see, it's literally just pretend that y and z are constants. So that's the difference. So it's really not that big a deal to do a partial derivative in comparison to a regular derivative. You're just pretending that the other variables are constants. Anybody have any questions with that? All right, I'm going to go ahead and split unless anybody stops me. So,
Mr. Younger.
Yes.
Yeah, I joined back because I had a quick question.
Yeah,
So
go for it.
for the midterm, review chapters 1 through 7, correct?
I'm leaning towards including 7 right now. So yes, I would definitely start doing that. The practice test will be your best way, and looking over any past homeworks or any past concept questions, stuff like that. But you'll have a practice midterm, and that should be ample practice for you. Just do it as
Okay.
many times as you can.
Is it similar to like, the practice test? If you keep retaking that over and over and over and over again, like you are most likely to get a good grade on the real online test? Is it similar
Yeah,
to
I
that
tell
like kind of
people
thing?
that if you can do 3 or 4 in a row without looking up more than say one of those questions and consistently scoring an 80 or higher, you're probably in a pretty good spot. If you can't do 3 or 4 in a row without looking up more than one, you probably need some help. And if you're making less than 80s, you definitely need some help as well. So yeah, that's a pretty good rule of thumb. There is a lot of questions in that bank though, so you could take it probably 100 times and not see all of the questions, but you can see a lot of them.
Okay, and then for the midterm, is it multiple choice similar to the practice test, or is it
Usually the midterm is multiple choice, but occasionally it'll have 1 or 2 problems where I'll say, okay, like if it was an online test, which is not, it'd say, all right, now turn in your work neatly done. You've got 15 minutes after you turn in the test to do it. Sometimes I do that so I can give you a little partial credit to make sure you can do some big problem. Like in the first semester, it might be a problem where you're going to have to divide one equation by another to eliminate a variable, or where you're going to have to add vectors by hand or something like that. So occasionally I'll have something like that, but generally it's just all multiple choice, and there's usually on the order of 20 to 25 so that y'all can miss a couple without getting a C.
Okay, sweet, awesome. And then for the midterm practice test, it's gonna be released this week, or is it already?
Yeah, it definitely should be hopefully sometime tomorrow. I apologize again for not having it ready yet, but I cannot imagine it taking more than tomorrow. But I'll send out an announcement and an email to everybody when it goes out. I think when I send announcements, you guys get to see it. So hopefully y'all have seen announcements and all that stuff.
Okay, cool. And then last thing, sorry for
problem.
drilling you. I sent you the lab 7.
Yeah, I got it.
Okay, awesome.
Yeah.
Yeah, that's everything.
That's it. All right. See you, John.
Awesome. You have a great spring break.
You too.
Thank you. Bye.
You're welcome. Thank you. Bye-bye. Mariana, George, Alvin, I'm getting ready to say bye unless you let me
I'll
put up.
stop you.
Okay, go for it.
So I'm not sure if you could do this, but is it okay if I could have a chance to take tests chapters 5 and 6? I wasn't able to attempt at them last Sunday. I just completely forgot and just didn't do it.
Is this George?
Yes.
Yes. It turns out you're just so lucky that I did, in fact, open up that test 3 again, and you have until I think the 14th at midnight, 11:59.
Oh, so you opened test 3. Sorry, I thought when you were talking about that earlier, you were talking about chapters 3 and 4.
Nope. I opened practice test 3 and test 3 until March 14th at 11:59. So you are
okay.
golden, sir.
I see. Thank you.
No problem. I was seeing now that Taylor Fontaine said so many G's, the poor child. That's great. On the displacement variable. That's great. All
Well,
right.
thank you, Mr. Younger, and I hope you have a great spring break.
Thank you. I hope you do too. All right, last call. I'm looking at the chat too, just in case someone's trying to frantically type something to keep me from signing off. It does not look like Mariana or Alvin are trying to do so. I'm going to stop share, and then I'm going to, in fact, end the Zoom meeting. Still nothing. All right, well, you folks have a great spring break, and I can't wait to see you the Monday thereafter. Talk to you later. Bye-bye.